visible, but now suddenly it gone off. Now it is coming, so make it full screen.
Okay, sir.
Make it full screen. You go to slideshow and make it full screen. You go to slideshow, and now it's coming up.
Good afternoon, good evening, everyone. I am Priyanka Agrwal. My topic of presentation is reliability investigation of interfacial defects in indium gallium arsenide silicon on insulator field effect transistor FinFET for high performance applications. These are the outlines. Firstly, we will discuss the interface trap charges in indium gallium arsenide silicon on insulator FinFET structure, and then we will analyze the results. Now we come to the introduction. To improve the performance and density, MOSFET channel length and other parameters have been forced to decrease. Some of the topologies in place of MOSFET we can use are 3D multi-gate transistors, transistor known as FinFET. FinFET is basically fin-like structure, field effect transistor. In this study, we will investigate the reliability of interfacial defects in indium gallium arsenide, silicon on insulator, FinFET, field effect transistor for high performance applications. Why we are using FinFET? The reason for using FinFET, it is helpful in minimizing or mitigating the short channel effects, and also the leakage current also reduces. Switching speed is also high, and drive current is also better. Excellent electrostatic control over the channel. In this FinFET, we are using the compound material that is indium gallium arsenide. By using the indium gallium arsenide, the benefit is it provides direct band gap, high carrier velocities, higher electron mobility. High electron mobility provides a better electric field and superior linearity performance, low noise figure, and high gain. As we can see in the slide, this is the design for FinFET, 3D structure of FinFET. In the figure 1, in the figure A, we can see the source and drain and the gate contact interface. Also in figure B, it is the 2D view or cross-sectional view, cross-sectional view of the uh, indium gallium arsenide SOI FinFET structure. Here we can see the interface trap charges. By red color, it is showing that interface trap charges are present at the oxide interface at oxide and metal. These are the parameters for device constructions. In this device, we are using the channel length that is 7 nanometer, source and drain length that is 5 nanometer, fin height and fin width ratio that is 2, and oxide thickness is 1 nanometer. Here we are using the channel doping very high and source and drain doping is very high because it helps to reduce an impact ionization. Permittivity of high K dielectric, that is hafnium oxide, it is very high, which is 25. It helps us to reduce the short channel effects, and gate electrode function is 5 electron volt. Here, this is the result and discussion section. In this, we can see the drain current and gate to source voltage, the graph between drain current and gate to source voltage. For conventional FinFET, it is showing the diverting manner, and in the indium gallium arsenide SOI FinFET, we can see it converges. The improvement, it shows the improvement. Our devices uh, shows the drain current improvement. Next, the transconductance. The graph between the gate to source voltage and transconductance also improved in conventional FinFET and indium gallium arsenide SOI FinFET, as we can see in this figure and also in this figure. for the same drain to source voltage and channel length and oxide thickness, but the material is different. Here we have used the silicon and here we have used the compound material. We can also see the switching ratio. Switching ratio is the ratio of I on and I off current, that is also known as drive current. Here in this graph, in the first figure, we can see the switching ratio of different devices, conventional FinFET and indium gallium arsenide silicon on insulator FinFET. The design device shows better switching ratio comparison to conventional FinFET. And also the figure B, we can also see the sub-threshold swing. That is also a kind of short channel effect. It is also improved in indium gallium arsenide SOI FinFET. Sorry, it is minimized because it is a kind of short channel effect. Now the surface potential versus distance along the channel. It also, we can also see the conventional FinFET also shows in figure A the graph that is below indium gallium arsenide silicon on insulator FinFET, and also DIBL, brain induced barrier lowering, is also a kind of short channel effects. The short channel effect is something which occur when we reduces the channel length or the size of a device. When we minimizes the channel length or source, drain and gate distance, these short channel effects occur. One of a kind of short channel effect is also a DIBL. In conventional FinFET, it is high, and indium gallium arsenide SOI FinFET is low. Here we can see the electric field, as I have already told in the previous slide, that the electric field increased in the compound semiconductor used FinFET is also increased due to the higher electron mobility, and in the conventional FinFET it is low. And also the we can see the graph B, where we can see the electron mobility that is also high in the indium gallium arsenide SOI FinFET. We can use the this application for electric field, high electric field and high electron mobility for the RF application also. Along with the linearity performance, it also can be used for RF applications. So this is the conclusion. As we have discussed the interfacial defects, using the interface trap charges, we can control we can minimize or we can optimize the defects. This work provide valuable insight into the defect mechanism and offer guidelines for improving the fabrication process to achieve more reliable high performance. And we identify also the minimum interfacial defects. These are the references, and thank you.
So is my screen visible?
Yeah, it's now visible.
Okay. Good evening, everyone. It is a pleasure to present one of my ongoing work at the International Conference on Composite Materials for Environment Protection and Remediation. Today, I'll be discussing on and addressing on one of the pressing environmental issues that we face. Specifically, I would like to withdraw into Specifically, I would like to withdraw onto a novel activated carbon-based nanocomposite using that has been used to degrade 4-nitrophenol from wastewater material, from wastewater. Water pollution is one. Water pollution is a critical global issue, with 4-nitrophenols being one of the most hazardous compound that is present in the water. And this compound has been discharged into the environment through various sources. And these are some of the sources which you can see on the right side of the screen, such as pharmaceuticals, petrochemical manufacturing, pesticides, synthetic dyes, wood preservation operation, leather industries, due to which it has an adverse effect on human health, and the aquatic life that is present on water. Because this compound is not only toxic but has an carcinogenic character, and exposure to such compound can cause injury to blood cells, damage to the central nervous system, and poses mutagenic effects to the organism. Not only that, it has an adverse acute as well as chronic impacts on human health, which leads to vomiting, sore throat, difficulty in swallowing, skin and eyes irritation, so and so forth. Therefore, this compound is considered to be as a priority pollutant by the United States Environmental Protection Agency with a maximum allowance contribution concentrations of 1 to 20 parts per billion. In order to remove these organic pollutants from water, there has been several methods that has been used over the years, and these are some of the methods that I would like to address in this lecture, such as adsorption, coagulation, ozonation, so and so forth. Although these methods has been successful in removing 4-nitrophenol from water, but there are some concerns related to these methods because it has led to the secondary waste generation, operation difficulty, reliability, pre-treatment requirements, environmental impact, formation of toxic byproducts. So in order to deal this kind of issues, photocatalytic degradation was found to be a good method which helps in eliminating the organic pollutants efficiently, converting the pollutants into less harmful compounds, minimizing the solid disposal issues, and it is very cost effective and sustainable in nature. So how does this photocatalytic degradation takes place? This photocatalytic degradation takes place in the presence of light, where the semiconductor material absorbs the light and it transfers the electron, where an electron has been promoted from the valence band to the conduction band, and thereby creating an electron on the conduction band and a positive hole on the valence band. And this electron behaves as a reductance, which is the phenomenon of photoreduction, and the positive hole acts as a oxidant, which is the phenomenon of photooxidation. There are different kind of metal oxides that has been used, and these are some of the metal oxides which I would like to show. Zinc sulfate, titanium dioxide, copper oxide are some of the metal oxides, out of which zinc oxide has been used extensively for my present work because of its non-toxic nature, stability, eco-friendliness, and low cost. However, there are some concerns related to zinc oxide, related to the use of zinc oxide because of the photocorrosion and instability when it is exposed to light. In order to overcome this kind of issue, zirconium dioxide has been doped in zinc oxide, forming zinc oxide zirconium dioxide complexes, which helps in increasing the generation of the OH radicals. Also, zinc oxide has a high thermal stability, excellent corrosive resistance, and a high dielectric constant, which helps the zinc oxide to avoid from to undergo such photocorrosion phenomena. There is another problem which we face during the preparation of this material, that is the agglomeration and high electron recombination. So in order to overcome this kind of issues, what we have done was that we have used a supporting material, and in our study we have used activated carbon as a supporting material, which we have synthesized by using a biomass material that is available at the vicinity of our campus. So why we have used a supporting material? Because it effectively separates out the degenerate electrons from the holes, which is the main purpose, and also it helps to enhance the dispersion of zinc oxide species, thereby reducing its agglomeration property that is present on the material. So these are the main reasons because of which we have used the supporting material. And activated carbon, because of its high porosity, high physiochemical stability, abundance functional groups, so and so forth, helps in taking, which helps to avoid those properties issues relevant to this nano photocatalyst. So coming back to the materials and methods, this to prepare the activated carbon, I have used a biomass material such as cotton cautus biomass, which is locally available in our campus. Then we have done the activation by using a QH, and then we have doped with zirconium dioxide and zinc oxide, making a composite using a hydrothermal method. And then this composite was formed, and this composite was further sent for characterization. These are some of the characterization I have done, and there are some characterization for which I have sent the samples, but I have not received the data. But from these results, what we have found was that from the first FTR spectra, we can see that at 744 centimeters, 728 centimeter inverse, and 619 centimeter inverse, ZRO, ZNO, and ZNOR, OZR stretching vibration has been observed, which confirms that the nanoparticle has been formed. Also, with the XRD, we were able to calculate the average crystalline size using Debye-Scherrer equation. Also, with the help of the TEM, we were able to calculate the particle size of the material, which was in the range of 21 to 44 nanometer. And with the help of the XPS, we were able to confirm the presence of elements such as carbon, oxygen, zinc, and zirconium. The more important thing here was also the PL studies, which we have done. And in order to see whether by using a supporting material, whether it will help in reducing the electron hole recombination, which we were able to confirm. And from here, this spectra, we were able to see that when we dope the supporting material with the composite material, we were able to see that there is a decline in the peak, which confirms that there is a the electron hole recombination rate has been reduced, implying that the composite materials has a higher photocatalytic efficiency. After that, we have done the degradation studies of the compound, for which we have considered some of the operating conditions. And under these operating conditions, we were able to find out 100% removal efficiency. Further, we have tried to study the efficiency with respect to the pristine zinc oxide and pristine zirconium dioxide. And from there, we have able to find out that the composite material was found to show highest removal efficiency as compared to the other pristine zinc oxide and zirconium dioxide. And in order to make the process more sustainable and to reduce the disposal cost, we have also done some regeneration studies. And from these regeneration studies, we were able to know that this material has an outstanding utilization capacity even after numerous cycle, which I would like to show here, that on the first cycle, we were able to find 100% removal efficiency. But as we increased the cycle, till the sixth cycle, it was still showing a good removal efficiency. In order to incorporate with the experimental study, we have done some theoretical studies so that it will help to save the overall cost and increase the efficiency. Using this density functional theory method, we were able to optimize the structures, and we were able to study the homo-lumo band gap. And from the studies, we were able to confirm that the prepared material was found to show a lower band gap as compared to the zirconium dioxide and zinc oxide nanocomposite. So in conclusion, I want to mention that the biomass material has been used as an activated carbon, which was doped with the zirconium dioxide, zinc oxide nanocomposite, and it has been developed using a hydrothermal technique. This method has been used for different analysis, and from the XRD analysis, we were able to confirm the composite material, and also the crystalline size of the material was found to be 39.41 nanometer. We have also done some regeneration photodegradation studies, and from the studies, we were able to find out that 100% removal efficiency was observed under these operating conditions. Also, we have done some multiple regeneration studies, which shows that a good results even after multiple cycles. And with the help of the density functional theory, we were able to find out that the prepared composite was found to be was showing lower bandgap as compared to the zirconium dioxide and zinc oxide nanocomposite. So thus, this confirms that the prepared material would serve as a promising photocatalyst for the degradation of 4-nitrophenol from an aqueous solution. So these are some of the references, and I would like to thank the organizing team for giving me this opportunity and privilege to present my work in this international conference. Thank you, and
PhD scholar, Tameti University. Sir, my topic is an overview of magnesium matrix composite. And as a waste material is considered to a reinforced material. Sir, first of all, I would like to discuss some brief discussion of magnesium alloy. Magnesium alloy is a lightweight material as compared to other, because the density of this material is very low, and it's 1.738 gram per centimeter cube, which is, if we consider to other material, which is 2/3 of aluminium, 1/4 of cast iron, and 2/5 of the titanium alloy. Due to this low weight density, it also have various characteristics: low density, superior dimensional stability, exceptional shock absorption capability, and excellent electromagnetic shielding. Sir, this is the slide in which we compare the magnesium material to aluminium, titanium, and steel. In density, it's a very low density, 1.74 to 1.87 gram per centimeter cube, sir. In aluminium, if we see that, it is the 2.55 to 2.85. And if we see in titanium, that is higher than 1.2 and 4.5 to 4.9. In steel, it is very, very high, 7.5 to 8. And in other characteristics, yield strength, if we compare in yield strength, the magnesium alloy have 70 to 215 megapascal, and aluminium has 50 to 350, and titanium have 700 to something 1200. In steel, it is 180 to 1050. So elastic modulacity, we compare that, it have 40 to 47 gigapascal, and in aluminium it have 70 to 95, in titanium 100 to 120, and steel have the 190 to 200. So if we compare in melting point, it have low melting point 450 to 650, and in aluminium it have 485 to 690, and in titanium the melting point of 1485 to 1690. In steel it has a 1380, and in elongation comparison it have 0.8 to 10%, and in aluminium it have 0.5 to 10, and titanium 5 to 10, sir. And if we see in steel, it is the 5 to 70, very high, sir. In next, if we compare on magnesium alloy as a application field, sir, it is a very trending material. Now it is using in every field. We see there in automotive sector, it is used as the support to make the support bracket for brakes, clutch, and housing for a transmission system. It is also used in aerospace sector to make the landing wheels, because that low weight helicopter rotor fitting, gearbox housing, sir. In industrial application, it is considered to make the operating machinery such as textile machines. It is also considerable in electronics applications, sir. Electronics applications include the electronic packaging, hard drives, arms, cell phone, and portable media devices, device housing, sir. Now it is also using in the medical field, because the density is very low. It is using a portable medical equipment, wheelchairs, a cardiovascular stent, and orthopedic devices, sir. Now, in magnesium, sir, it have some limitation as compared to metal matrix. It have low strength and wear resistance, poor corrosion resistance, low high temperature strength, sir. Due to these limitations, researcher developed the magnesium metal composite (MMC) by adding the reinforced material. So now I would like to discuss the reinforced material. Reinforcement material. If we add any reinforcement material to to aluminium alloy, sorry, magnesium alloy, it enhances the characteristics of the material. There are the list of some reinforcement materials, sir. Aluminium oxide, silicon carbon carbide, and boron carbide, titanium diboride, carbon nanotubes, and graphene. But these reinforced materials are very conventional materials and generally used. But in this paper, I would discuss only say solid waste reinforced material. So solid waste reinforced material are used as a reinforcement in magnesium metal composite to enhance the property of the magnesium alloy. Sir, I have read the literature review in which I have found that XL is also used as the reinforcement material in magnesium alloy. C-cell also considered in as a reinforcement material. Fly ash also considerable to enhance the property. Rice ash also be considerable. Sir, waste glass is also be considerable to enhance the property, and red mud. This is similar other material also be there, sir. Now, if we compare if we discuss the chemical composition of the waste material, if we see there, sir, XL have aluminum oxide 18% aluminum oxide, and fly ash has the 25.4% aluminum oxide, sir. If we can talk about calcium oxide, then red mud have 21% calcium oxide, fly ash has 6% calcium oxide, and magnesium oxide 1% in fly ash. Sir, potassium oxide 0.65%, titanium oxide in red mud it have 7.4, in fly ash 0.53, and in sodium oxide, sir, 4.75, and in fly ash 0.47. So calcium carbonate in red mud it have 95.5%, sir. So due to these characteristics, we can also be considered as a waste material if, in magnesium metal matrix. Sir, now if we discuss some basic technique to fabricate the MMC material, steel casting and powder metallurgy. These are the traditional technology, traditional fabrication method to make the metal manufacturing metal matrix. In steel casting fabrication, particle reinforced material composite. In this process, stirring reinforced ingredient element into the molten metal as a primary step, and it is the producing of the composite. This is the figure diagram which is show the process of steel casting. This is the electric panel stirrer. This is the molten foam cabin, molten material. This is the electric furnace and the blower. So this is the process, simple diagram to give the presentation of steel casting. Sir, powder metallurgy. Powder metallurgy is a traditional manufacturing process that produce precision and highly accurate part by pressing the powder metals and alloy into a rigid die under the extreme pressure. This is the overall diagram, sir. Process flow diagram: mixing or blending of powder, compacting of the powder, powder sintering. It may be hot and cold sintering, sample preparation, and then final characterization. This is the method, sir. Now I have read, sir, some papers and find some conclusions. Base material, if we consider some base material, aluminum oxide, fabrication process, the outcome was there, mechanical and wear property increase at 3 different volumes, fraction 0.5, 0.66 volume, percent 1.66 percentage volume, 1.12 and 1.5.
Please try to finish it by 1 minute, okay?
Sir. Sir, these are the overall conclusion. I have read the number of papers, sir, in which we have seen that if we add some reinforcement material in a base material, then definitely characteristics of the base material is also enhanced. Sir. So this is the overall conclusion. So these are the references in my research work and in my paper, sir. Thank you, sir.
Okay, sir. Good evening, everyone. I'm Tejashwini D M, research scholar, working under the supervision of Dr. Nagaswarupa HP, Professor and Chairman, Department of Studies in Chemistry, Davangere University, Davangere. Today, I'm here to present my work entitled Green BZF Nanocomposites for Electrochemical Sensor Applications. These are the contents of my presentation as shown in the slide. Introduction includes a greenly synthesized BZF bismuth zinc ferrite nanocomposite that possess unique properties like tunable size with the enhanced active sites compared to that of the counterparts of the bismuth zinc ferrite nanocomposites like bismuth oxide and zinc oxide. Bismuth zinc ferrite nanocomposite that shows superior properties, whereas BZF nanocomposites have excellent selectivity and sensitivity property that plays a major role in the sensing of biomolecule like urea. The objectives of the current work are designing and development of bismuth zinc ferrite nanocomposite by solution combustion method, followed by the fabrication of a modified carbon paste electrode using synthesized BZF nanocomposites for electrochemical sensing of urea. So here, the bismuth zinc nanoferrates were synthesized by solution combustion method that includes the stoichiometric quantity of bismuth nitrate, zinc nitrate, and ferric nitrate as an oxidizer and reducer as a aloe vera extract that we are using. So we are taking it in a stoichiometric quantity, and the formation of the redox mixture will be found. Next, the redox mixture that are stirred for 10 minutes under the magnetic stirrer, and the obtained homogeneous mixture that are placed in a preheated muffle furnace at 530 degrees centigrade for 3 hours. After the combustion process, the BZF nanocomposites were obtained. So further, this BZF nanocomposites were subjected to the calcination process at high temperature of 950 degrees centigrade for 3 hours, 3 to 4 hours, in order to remove the water content or the impurities present in the BZF nanocomposites. Whereas after the synthesis of BZF nanocomposites, they are subjected to the characterization techniques like XRD, FTIR, UV-DRS, SEM, EDAX, and TEM analysis. The results obtained from the XRD analysis were average particle size around 27 nanometer, that is calculated by Debye-Skerer's equation, and the confirmation of formation of the BZF nanocomposite that matches with the JCPDS card number 720398 and 742397. The FTIR analysis that shows the expected functional group present in the PZF nanocomposite, where the bismuth oxide or ferric oxide that are present in the fingerprint region of 624 per cm, whereas the SIBO stretching that are found at 1109, where the trap nitrates that are found at 1368, and the carbonyl or the OH vibration that are found at 2172, 2362, and 2883 per cm. The UV-DRS analysis that is exaggerated as UV diffuse reflectance spectra analysis is implemented for analyzing the energy band gap for the synthesized PZF nanocomposites between the wavelength range of 200 to 800 nanometer, where the optical band gap, that is EG, of the synthesized PZF nanocomposite are very crucial, and in order to know the conductance and absorbance of the light, absorption of the light behavior by Kullbacher-Monks theory and Tox plot, we are computing the energy band gap that is found to be 2.73 electron volts for the synthesized PZF nanocomposites. The surface morphology of the synthesized BZF nanocomposites were evaluated by SEM analysis that is found to be flake-like structure, and the elemental analysis that are that is evaluated by EDAX analysis, where the element, in order to know the percentage purity, where the expected elements are bismuth, iron, zinc, and oxide. Whereas in order to know the surface topology of the synthesized BZF nanocomposite, TEM analysis was carried out that shows a irregular morphology, and the interplanar distance between the atomic layers can be analyzed that shows 0.0191 nanometer by TEM analysis. further, they are implemented to the electrochemical studies, where that includes the fabrication of bismuth zinc ferrite based modified carbon paste electrode. The homogeneous carbon paste electrode were created by grinding the graphite powder and active material as BZF nanocomposites, and the silicon oil as a binder in a mortar for around 30 minutes in the ratio of 70:30. This results in the development of carbon paste. That paste were filled in a Teflon tube with a 3 diameter, where the polished copper wire that are inserted inside the carbon paste electrode as a holder, as shown in the figure. As the BZF based carbon paste electrode that were filled and that are polished by using butter paper. And by implementing this bismuth zinc based modified carbon paste electrode with a 1 molar HCl as a suitable electrolyte, electrochemical properties were examined, where the scan rate ranging from 10 to 15 millivolts per second. The oxidation and reduction peaks were observed that demonstrate a fast transport of electrons at the point of contact between the electrolyte and the working electrode. The specific capacitance that are found to be 251 Faraday per gram for 10 millivolts per second and 146 Faraday per gram for 20 millivolts per second, and 105 Faraday per gram for 30 millivolts per second, and 76.8 Faraday per gram for 40 millivolts per second, and 76.3 Faraday per gram for 50 millivolts per second. As increased in the scan rate, the decrease in the specific capacitance can be observed. So further, the electrochemical impedance analysis can be done, where the synthesized BZF-based modified carbon paste electrodes conductivity and charge transfer capacity were measured by Nyquist plot as shown in the figure, and the corresponding circuit diagram that are inserted inside that is shown in the figure. In order to determine the selectivity and sensitivity of the synthesized BZF-based nanocomposite based modified carbon paste electrode, the sensing application for urea is conducted, where as shown in the figure depicts that bismuth zinc ferrite nanocomposite based modified carbon paste electrode that are implemented to the cyclic voltammogram for detecting urea. The constructed electrode that shows a considerable change in the oxidation and reduction peak, indicating that it might be employed for a sensing of urea from the concentration between 1 mm to 5 mm, where the electron gain at the cathodic peak of minus 0.019 volts as well as the broad peak at 0.47 volts, followed by the electron loss at minus 0.4 volts as an anodic peak for the synthesized bismuth zinc ferrite nanostructure that are synthesized by aloe vera as a fuel, and the the bismuth zinc ferrite nanocomposite amperometric curves are shown in the figure B, that displays a sensitivity towards the urea, which is achievable at this sweep rate ranging from 1 to 5 volts in 5 mm concentration range. The addition of urea continuously decreases the redox peak current. So this phenomenon might be the cause of buildup of the additives on the electrode exterior surface, which leads to the drop of the number of the active sites present on the surface of the electrode. As an outcome, the bismuth zinc ferrite nanocomposite based electrode, modified carbon based electrode, displays a significant improve in the electrochemical activity at 1 molar HCl as a suitable electrolyte. So the conclusion of the current work in the present work, the bismuth zinc ferrite nanocomposites were successfully synthesized by combustion method using aloe vera as a fuel, where the synthesized bismuth zinc ferrite were confirmed by the XRD FTR, UV-DRS, SEM and EDAX analysis, and TEM analysis. Electrochemical activities were studied by integrating bismuth zinc ferrite composite-based modified carbon paste electrode. Detection of urea was evaluated by employing bismuth zinc ferrite composite-based modified carbon paste electrode. So these are the references I gone through for the above studies. Thank you.
Good evening to all. My name is Mukesh Kumar. I am research scholar of JP Institute of Information Technology, Noida. I present my research work entitled of sensitivity analysis of a gallium arsenide, gallium antimony, heterojunction photocatalytic TFET-based biosensor. This is the outline of my presentation: introduction, proposed TFET biosensor, result discussion, conclusion, and references. Biosensor is an electric device that converts the biological response into measurable response. In the present time, biosensor use in many fields like diagnosis of disease, food processing, environmental monitoring, industrial use. Figure 1 shows the basic block diagram of a biosensor. Here is an analytic that the biomolecule that we want to detect the bioreceptor that detach the bioreceptor attached to the biomolecule to the transistor. Transistor convert this biological response into the electrical signal. Its signal may be very low, to need the processing unit and electronics device that can process, and the signal sent to the display device. Based on the transducer, biosensor can be categorized as an electrochemical biosensor, optical biosensor, mass-based biosensor, calorimetric biosensor. Suppose biosensor in category the potentiometric biosensor is the category electrochemical biosensor. TFET biosensor, FET biosensor, first FET-based biosensor discovered in the 1970. It is the ion sensitive field effective transistor-based biosensor in detect the biomolecule based on the charge property. After that, the 1982 first FET-based biosensor produced to glucose detection. After that, the in 2012 first DM TFET-based biosensor proposed by Professor R. Narang. After that, the TFET biosensor get a lot of attention to the researcher based on the high sensitivity and fast response. Figure 3 shows the basic cross-section of TFET. TFET is a PIN structure. It is a doping constructor of drain and source region are similar but opposite polarity. TFET operate on the band-to-band tunneling, not rather than the diffusion. Figure 4 shows the proposed TFET gallium arsenide, gallium antimony, heterojunction TFET biosensor. Here is the TFET basically suffer from two major issue: low on current and bipolar current action. In this research, we consider this limitation. We use the gallium antimony for the low band gap material in source region to improve the on current, and high band gap material used in the drain side to reduce the ambipolar conduction. Here the device, here the table 1 shows the dimension of the proposed device, and here is the active layer doping concentration 10 to power 15 atom per cm volume. Here TFET device, FET device also suffer for the complexity of fabrication. So hence here use the polarity control technique to introduce the drain and source region in the proposed device. Here PG1 used to drain region. When apply the positive terminal as PG1 terminal, he develop a N type region, and PG2 you apply the negative supply to induce the P type region. Figure 5AB show the band diagram of the proposed TFET device. Here you can see the when the control gate voltage CV is 0, not applied, the band bending not possible. The tunneling variable is very high, so tunneling probability not happen in this way. When apply the gate voltage on the control gate terminal, the band bending line and the tunneling possible in this case. And in the proposed biosensor, we target the band bending modulation to detect the biomolecule. Before the use the device, this device to as a biosensor compare and calibrate the proposed device to the references. Here can figure C 5.6 and see the proposed device transfer characteristics and reference device almost similar. Hence, this figures calibrate and authenticate the our simulated device. Figure 6 show the proposed gallium arsenide, gallium antimony heterojunction TFET biosensor. Here the capture the biomolecule, create the cavity and source region near to the tunneling junction to modulate the tunneling probability of the proposed TFET. In the simulation, the different type of biomolecule with charge and neutral here is the dielectric based on the dielectric estimate and the charge density. The proposed device observe the carrier concentration, band binding, transfer characteristic. For calculation, the sensitivity of this device is the equation number 1. Here the Q1, Q2. Here Q1 when the proposed device electrical quantity, electrical characteristic uh, when the cavity filled with the different biomolecule, and Q2 is the electrical quantity of device when the cavity of the proposed device is empty, means air in this cavity. Result. This figure show the impact of neutral biomolecules in of the proposed device. Figure 1 show the carrier concentration. Figure B show the band diagram. Figure 1 is consider the when the K of biomolecule increases in the cavity region, the carrier concentration in the source region increases and band bending increases, and the tunneling of charge carrier happen with when increase the K of biomolecule. Figure C show the transfer characteristic of the proposed device. Here the transfer characteristic, it can be see the when the increase the K value of biomolecule, the drain current of the device increases. Because the when the fill the cavity with different K value, the coupling capacitance between the PG2 terminal and source region increases, and the controllability of the PG2 terminal increases in the over the source region, and the control the carrier concentration in source region, hence the device on current increases. Figure D show the sensitivity of the proposed device, sensitivity calculated from the equation 1. Here you can see the sensitivity of the device for neutral biomolecule increases with increase the K value of biomolecule in the cavity region. This slide shows the charge biomolecule impact of charge biomolecule on the proposed biosensor. Here can say the figure 1 in the negative charge density in the cavity region of biomolecule increases, the whole concentration in source region on the surface of yes dielectric constant dielectric.
Please try to wrap up by 2 minutes.
Okay. When the negative charge density increases, the device on current increases. Figure D and E show the impact of ion sensitivity. Here say the when the negative charge density increase of biomolecule, sensitivity of the device increases. When the positive charge density increase in the cavity region, the device sensitivity decreases. Impact of temperature variation on the sensitivity. Here the two phenomena occur when the sensitivity on the increase the temperature. First, the on current increases is very small in the because the on current of the proposed device depend on the band to band tunneling, not the diffusion. Here the off current also increase due to the manual carrier concentration. But the sensitivity of the proposed biosensor decreases because when they increase the temperature, the biomolecule dielectric constant also decreases. Hence, the sensitivity of the proposed device increases. This figure show the impact of non-ideality of the proposed biomolecule. The previous study, we can assume the cavity of 100% filled with a biomolecule, but it will not happen all time. When the biomolecule in the cavity, may some blank space of some cavity may be empty. Here we consider the four different partial structure of convex, concave, increasing and decreasing of the structure. Here, the sensitivity when the sensitivity of the proposed biosensor high in case of the concave and decreasing iron because the biomolecule near the tunneling junction high. Similarly, impact of fill factor here consider here taken up for step 50%, 20, 50, 25%, 50%, 25%, 100%. Here consider the sensitivity of biosensor increases increase the fill factor of the biomolecule in the cavity region. This is also the comparison of the here comparison the sensitivity of proposed biosensor with previous proposed devices. Here can see the device of the proposed device so the high sensitivity compared to previous reported TFET biosensor. Conclusion: proposed biosensor can be here investigated only the on current, but we also we use the threshold voltage slope on current transconduction for sensitivity. Proposed biosensor also higher sensitivity with increase the evaluate biomolecule molecule. In sense, the results show that the proposed device can be better choice for the future bioequipment development. These are the references. Thank you.